So today I would like to multi-frequency power analysis in the brief amount of time we have. So let's consider a generic circuit element. Where this is the voltage drop across it, and this is the current flowing through it. And let's say that V of t is a function Vm1 cosine omega 1t plus theta V1 plus Vm2 cosine omega 2t, plus theta V2. And we are also going to have a multi-frequency current. Im1 cosine omega t plus theta I1 plus Im2 cosine omega 2t plus theta I2. So the instantaneous power absorbed by this impedance, resistor, capacitor, whatever you want to call it, is simply the product of these voltages and currents. And so what's going to happen, I'm going to call this guy V1, this guy V2, similarly, this guy I1, and this guy here, I2. And so we should be able to see that the power absorbed by this element is V times t, or V of t times I of t, which will become V1 I1 plus V1 I2 plus V2 I1 plus V2 I2. So we have four different power terms here, and they're all going to be operating at different frequencies, right? So we're going to be using the trigonometric identity. Cosine angle 1 times cosine angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2 to figure out what exactly is going on here, all right? So if we apply this identity, we can see that, let's look at the V1 times I1 term, okay? So just doing the V1 times I1 term is going to give us 1/2 Vm1 Im1 cosine omega t plus theta V1 minus omega 1t plus theta I1. So when we take the difference of those two angles, what we're left with is cosine theta v1 minus theta I1. So we're getting a DC term to start off with, plus 1/2 Vm1 Im1 cosine twice omega 1 t plus theta v1 plus theta I1. So our first product term gives us a power at two different frequencies. One is at 0, so we have a DC term, and the other one is at twice omega 1. We're going to add to this the product of V1 and I2. So that's going to be 1/2 Vm1 Im2 cosine. And so now we have the angle omega 1t plus theta v1 minus omega 2t plus theta I2 is going to give us a frequency term that is the difference. So we're going to have omega 1 minus omega 2t plus theta v1 minus theta I2. So this is a third frequency. And then we're going to have 1/2 Vm1 Im2 cosine. Now we add these guys together. So omega 1 plus omega 2t plus theta v1 plus theta I2. And so we're only halfway through, but we're already at 4 discrete frequencies, right? So instantaneous power in a multi-frequency circuit, the number of frequencies that the power oscillates at grows very, very rapidly. We should see we're going to wind up, I believe, with 5 different frequencies, and I'll explain why it's only 5 momentarily. But if we had 3 different frequencies, I think we'd wind up with 10. It grows very, very rapidly. So the multi-frequency power analysis kind of gets out of hand pretty quickly. All right, so now let's look at the V2 times I1 term. So that's going to be Vm2 Im1 cosine. So now we're going to have omega 2t plus theta v2 minus omega 1t plus theta I1, which is going to give us omega 2 minus omega 1 t plus theta v2 minus theta I1 plus 1/2 Vm2 Im1 cosine omega 2 plus omega 1 t plus theta v2 plus theta I1. So let's take a look at these guys real quick. All right. So the second term of the V2 times I1 portion and the second term of the V1 times I2 portion actually operate at the same frequency of omega 1 plus omega 2. So that's, these two guys could be combined into a single frequency term. But what about the left-hand portion of the first term? So we have one that's oscillating at minus omega 2t, and the other one that's oscillating at omega 2 minus omega 1 times t. So these are actually oscillating at the same frequency as well, because the cosine of x is the same as the cosine of negative x. So we could treat this one as, if we put a negative sign here, and a negative sign there. So we're multiplying that angle by a factor of, the angle only by a factor of -1. That would actually give us omega-1 minus omega-2 minus theta V2 minus theta I1. So we see that it's actually oscillating at the exact same frequency. So we could add those two terms together as well. So now we've gone through 3 multiplication parts, but we're still only working at 4 different frequencies. And then lastly, when we do V2 times I2, we're going to have 1/2 VM2 IM2 cosine. So here we have omega-2 plus theta V2 minus omega-2t plus theta I2. So the omega terms cancel out and we simply have theta V2 minus theta I2. So we get another DC term here, plus 1/2 VM2 IM2 cosine, actually, twice omega-2t plus theta V2 plus theta I2. And here's where our 5th frequency comes in. So our last term is operating at twice the frequency of omega-2. So big and ugly and gnarly, but what if we wanted just the average power? How could we determine that? Any thoughts? Yeah, it's the DC terms, absolutely right. Because we're going to see that all these other AC terms, so mathematically, we would need to integrate this guy, right? And we would need to integrate it over one period of its waveform. So let's just say, for the sake of argument, that omega-2 is an integer multiple of omega-1 to make the math easier. So what that would mean is that if I only integrated over the interval, or excuse me, over the period of the frequency oscillating at a frequency of omega-1, because everything else is integer multiples of that specific frequency, that would mean that when I oscillate, or excuse me, when I integrated, say, this last term that's operating at twice omega-2, I'm really multiplying at probably 4 or more periods, but it's still going to be an integer multiple of periods. So we should see that effectively all of these cross-multiplied terms where the frequencies don't specifically cancel each other out, when we take the integral over one period, all of those are going to go to 0. And what we're left with is simply 1/2 VM1 IM1 cosine theta V1 minus theta I1 plus 1/2 VM2 IM2 cosine theta V2 minus theta I2. Now, what's really interesting about this result is that is the exact, well, trying to think of the best way to put this. So typically speaking, we cannot use the superposition theorem to calculate power because power is not a linear quantity. Because it depends on the product of voltage and current, it is inherently nonlinear. So the power absorbed by a resistor, even in just a simple DC circuit, is the voltage squared divided by the resistance, or the current squared multiplied by the resistance. Both of those would be nonlinear quantities because it's not a linear relationship between the input signal and the power. But here we can see that if we just treat each frequency portion in a vacuum, the average power depends only on what's going on at frequency number 1 and only what's going on at frequency number 2. So we could take effectively just those magnitudes and be able to work out everything. We don't have to actually go back to the time domain and figure anything out there. So the average power kind of acts like it's obeying superposition even when it shouldn't, and it's because we're specifically taking the integrals over integer values of the period. Okay. So this is multi-frequency power in a nutshell. So on an exam or anything like that, I could never ask you what the instantaneous power was for a particular problem because it would just take too dang long to actually bother to calculate anything. The average power would be fairly straightforward to calculate. Any questions on this? I know it's a lot of ugly math, but the algebra is fairly straightforward. And again, recognize that, let me put some arrows here. These two guys operate at omega 1 minus omega 2. No, that's not right. I need to move that up. These guys operate at omega 1 minus omega 2. And these guys operate at omega 1 plus omega 2. So we could combine them into single terms. So instead of having 8 different terms, we should be able to pare it down to 5. All right. So that's multi-frequency power. Like I said, in a nutshell, we have 10 minutes before I need to leave. So let's review effective values really quickly because that's going to be a really big thing we're going to be dealing with. So before we can delve into the complex power relationships, we must first identify and define what the effective value of a periodic waveform is, specifically periodic voltage signals and periodic current signals. So this is a review from circuits 1. Let's say that I'm looking at a receptacle. Power receptacle or plug in our walls look something like this, right? So these 3 terminals have specific things. This guy down here usually has a green wire connected to it, and it's going to earth ground. This guy right here usually has a gray wire, and it is going to the neutral. And this guy right here actually usually has a white wire, but I can't draw a white line. And this is what would be called our hot wire. And so when we use a multimeter, to measure the voltage drop, draw that one as gray, across this guy, what do we see? Has anybody ever used a multimeter and figured out what voltage we get out of our receptacles here in the US? You know, well, 115 to 120, thereabouts. More often, the range would be between 110 and 120 volts. This voltage is an effective value. So let's call this 120. I can get this guy to change color. There we go. 120 volts And we need to signify specifically that it is an RMS value, because power here in the United States, so it means the voltage waveforms and the current waveforms, are oscillating at a linear frequency of 60 hertz. So as a time domain function, this voltage would be technically represented as Vt is equal to 169.706 cosine 120 pi t plus some phase angle theta v that depends on when we start measuring our circuit. This would be in units of volts. But to have to carry around all of that information would make most of the math and analysis in designing electrical systems far too tedious. So instead, what electrical engineers did is they developed the concept of an effective value. And all an effective value for a voltage waveform is a DC representation of that same signal that would deliver the exact same amount of average power to an arbitrary 1 ohm resistance, okay? So from this definition, we can see that the effective value for a periodic voltage then simply becomes the square root of the integral of the square of a voltage waveform divided by the period. And similarly, our current I effective uses the exact same relationship. 1 over t integral over 1 period of the square of our periodic current waveform. And these definitions, again, are purely based on the fact that we're looking for a DC value, right? So when we square our periodic function, integrate that square, divide by the period, and then take the square root, we're going to be left with a single number, right? There's going to be no time dependency left whatsoever. So it is effectively a DC value for voltage or current. So let's look at a simple-ish waveform. Well, that looks like garbage. Here's time. Let's call this V of t. Let's give it a peak value of, say, 5 volts. And let's say that every second, or excuse me, every cycle takes exactly 1 second. So because this is a periodic waveform, I'm saying that it's repeating this triangular wave shape once every second. We can actually find an effective value for this to use in simple power calculations and all that kind of good stuff. So let's think about how we can take care of this, at the very least, set up the integral and all that kind of stuff. So the period of this guy why is my pen being so particularly weird today? Is this 1 second. So we could split this guy up into 3 different integrals. So the effective value would look something like this. We would have the square root of let's see, the 1 over the period, so that's 1 over 1 second of the integral from 0 to 1/4 of a second of, let's see, what's that slope there? It's 5 volts per every 0.25 seconds times time. This quantity, square it. Then we would have the integral from 1/4 of a second to 3/4 of a second. So it has a slope of -5 volts every 1/4 of a second. It's time shifted by 1/4 of a second in the right direction. So that's going to be t minus 0.25 seconds. Square this whole guy. dt. And our third term will be the integral from 3/4 to 1. Our slope is increasing. So we again have 5 volts, 0.25 seconds. Actually, I forgot something here, I'm sorry. So I have my slope, and then I have the time shifted value. So I'm sliding that over by 1/4 of a second, but I don't have my y-intercept at that particular new point in time. So I would need to add the y value, or the voltage value here, which is 5 volts. Square this, there we go. We're gonna do a similar thing here. Positive slope 5 volts over 0.25 seconds. Sorry, and no, I already did that, sorry. I'm getting ahead of myself trying to finish up quickly. T minus 0.75 seconds because I'm sliding it over to here. And then my new y-intercept is minus 5 volts. Square this guy dt. And then we have something, this square root goes over all of this, that we could put in our calculator and compute the average value of, but I ran out of time. So this is the process that we would use for a piecewise function. In your homework regarding this material, I'm going to give you, I believe, 3 generic functions. So I give you a sinusoid, a square wave, and I believe a sawtooth wave. And you should see that they actually come out to have nice, neat, effective values. So from circuits 1, you guys should recall that the effective value of a sinusoid is simply the peak value of the sinusoid divided by the square root of 2. Well, it turns out that for a sawtooth wave, the effective value is the peak value divided by the square root of 3. It's just real simple relationships for all of the basic waveforms that we use in electrical engineering. So I'm going to have you guys effectively draw these. All right, so this is a review on effective values. So on Wednesday's class meeting, we will be able to get into complex power and all that entails. All right, see you guys on Wednesday.